All right, here's our last little piece of 4-9. We're going to continue talking about anti-differentiation, but this time add a little bit of physics in there. A lot of times, anti-differentiation is helpful for us to figure out the motion of an object. And so we know that the velocity is really the same thing as the derivative of position. So that means the position is the antiderivative of velocity. So maybe we know the velocity function, we can work it backwards now to find the position function. Same idea with acceleration. Acceleration is the derivative of velocity, so that means the velocity is the antiderivative of acceleration. If we know the acceleration, we can take the antiderivative and get the velocity, and so on. If the acceleration and initial values in my position and initial values in my velocity are known, then we're able to find the position function by anti-differentiating twice. So let's do a few examples here. Example number 5 says, a particle moves in a straight line and has acceleration given by this function. So we have the acceleration function. Its initial velocity, so that means v of 0, when time is 0, is -6 centimeters per second. And its initial displacement, so its initial position at t equals 0, it's at 9 centimeters. Find its position function. So we are given the acceleration function, and we want to go all the way to the position function. That means we should be able to take the acceleration and find the antiderivative to get velocity, and then take the antiderivative again to get to the position. So that's what we're going to do. We're going to take the antiderivative of acceleration so that we can get the velocity. And remember, anti-differentiation and integration are the same thing. So we're going to integrate the acceleration function, the 6t plus 4, with respect to time. I ended up using my power rules, adding 1 to the exponent and dividing by that new exponent to get a general velocity function of 3t squared plus 4t plus c. But that's a very general velocity function, and I want a particular velocity function. So do we have any initial conditions about our velocity? Well, yeah, didn't it say up above that our initial velocity when t equals 0, my velocity was -6? So then that means we should be able to find c and find an exact velocity function. So I know that c is -6, and now I know that the velocity at any time is 3t squared plus 4t minus 6. So now I not only have the acceleration function at any time, I now have the velocity function at any time, and I can figure out what my velocity or acceleration is at any moment. But I don't want to stop there. I want to find the position function. So now that we have the velocity function, we should be able to find its antiderivative or integrate it in order to find the position function. So that's what we're going to do now. I'm going to integrate my velocity so that I can get my position function. Using my power rule and simplifying, I got a position function of t cubed plus 2t squared minus 6t plus c. But that's a general position function, and I want an exact position function for what we're talking about. So do we know any initial position or initial conditions in my position? Well, I know when t equals 0, my position was 9. So that should help me plug in zeros for time and 9 for my position and figure out that c is +9. So now I have an exact position function of t cubed plus 2t squared minus 6t plus 9. I can find the position at any moment, I can find the velocity at any moment, and I can also find the acceleration at any moment, all by finding the antiderivative twice and knowing some initial conditions. All right, let's do another one. Here's our last example in 4-9. Example number 6 says, a ball is thrown upward with a speed of 64 feet per second. A speed of 64 feet per second at the very beginning. Isn't that kind of like an initial velocity? So can I really say that when t equals 0, my velocity is 64 feet per second? So that's an initial condition we might need to use later. And it says here, it's thrown from the edge of a cliff that's 80 feet above the ground. So at the very beginning, my position is 80. So isn't that an initial position? So when t equals 0, my position is 80 feet. So I have a couple different initial positions, or initial conditions, I should say. The question says, find its height above the ground t seconds later. So I need to find the height or the position at any moment. So I need to find a position function. And then it says, when does it reach its maximum height and when does it hit the ground? So we got to find a couple of different things in this equation. But the first thing we want to do is find the position function. So if we have a velocity function, we can integrate it and find the position. But I don't have a velocity function. If we have an acceleration, then we can anti-differentiate it or integrate it twice and find the position. So that's probably what we're going to need to do. So we know that the acceleration of any free-falling object, if we're in feet, is negative 32 feet per second squared. So I'm going to start with that idea. Remember, this is just a physics idea where we have the acceleration due to gravity is negative 32 when we're talking about feet, and it's negative 9.8 when we're talking about meters. So negative 32 feet per second squared is our acceleration of any free-falling object. So can I integrate that and figure out then what my velocity would be? So integrating it would give me a negative 32t plus c. But since I know some initial conditions in my velocity, I know that my initial velocity is 64, then can I actually come up with an exact velocity function of negative 32t plus 64? So that's my speed at any moment. But let's find position. So let's anti-differentiate, let's integrate my velocity so that I can find the position function at any moment. So I'm going to use my rules for anti-differentiation and find that my position is negative 32t squared over 2 plus 64t plus c. But don't I also know some initial values in my position? I know that my initial position was 80 feet. So I should be able to plug that in and find an exact position function of negative 16t squared plus 64t plus 80. And that should look familiar. We've talked about this before, where this is our initial velocity and this is our initial position. And so that should kind of look familiar. But now we have a position function, we have a velocity function, and we can answer the questions. So we've answered the height above the ground t seconds later. That's my position. But the second question says, when does it reach its maximum height? Well, if my position is my height and I want to find the maximum, haven't we found maximums before? Haven't we figured out when our derivative changes from positive to negative, that's a maximum? And if the derivative of position is the velocity, well, can I figure out when that velocity changes from positive to negative? But before I do that, I have to find my critical numbers. I've got to figure out when that derivative, the velocity, equals 0. So that's what I'm going to do. I'm going to take my derivative of position, which is the velocity. I'm going to set it equal to 0 so that I can find my critical numbers. I ended up getting a critical number of t equals 2. So at 2 seconds, I have a critical number. I'm going to test to make sure that that's a maximum and not accidentally a minimum. So I'm going to take my velocity. I'm going to plug in my on my sign chart the 2, and I'm going to test a number just less than 2 and a number greater than 2 in my velocity function. I'm hoping that my velocity goes from positive to negative because that will tell me that I've just found a maximum value. And that's what I wanted. I wanted to find the maximum height. When I tested values in my velocity, I ended up getting a positive and then a negative, so I do know now that it's a maximum height that happens after 2 seconds. I throw this ball, at 2 seconds, I've reached my maximum height. All right, the last part of the question says, when does it hit the ground? Well, I know that it hits the ground when my position is 0, right? So when my position is 0, so I can set my position equal to 0, and I can figure out when this ball will hit the ground. I can solve, I can factor, and I ended up getting t equals 5 and t equals negative 1. But you notice I've crossed off the negative 1 because it doesn't make sense for time to be negative 1 seconds. But it does make sense that t equals 5, and that means that the ball, or whatever this object is, hits the ground after 5 seconds. So I know when it hits the ground, I know when it's at its maximum height, I know its position, velocity, and its acceleration even, all by just having some initial conditions. Pretty cool, huh? All right, make sure that you practice all of those. This is the end of 4 and 9. The next thing we'll do is 5.1. Let me know if you guys need